Swayam Prabha. Digital India. Educated India.
So, hello students, welcome to the class 2 of this course, Thermal and Statistical Physics. So, quickly what we will do is we will recap what we did in the last class. So, essentially we started with the topic of kinetic theory of gases, and there what we did was we made some assumptions, right. So, we made some drastic assumptions like the gas molecules are dimensionless, they are like point particles essentially. They never interact with each other, but they only collide with the walls of the container, and the collisions with the walls of the container, they are always elastic, which means the kinetic energy of the system is always conserved, right. And since the potential energy element is 0, since there are no additional forces acting on these molecules, so we were able to derive a very nice looking expression for the pressure exerted by such a collection of molecules on the walls of the container, right. And the last time we saw we obtained an expression which is something like this. So, pressure equals 1 by 3 m n by v squared average, where m was the mass of a molecule, capital N was total number of molecules, and capital V basically was the volume of the container. And V squared average was, so root mean squared velocity of molecules, right. So, this was the expression that we got, and also we wrote it in a slightly different way. So, since m times n is the total mass of the molecules in the container, so we can write m times n by v as the rho, which is the mass density. So, this is also equal to 1 by 3 rho v squared average, and this is the expression for the pressure, right. So, today what we will do is we will basically introduce another very fundamental concept in thermodynamics, which is called temperature. Okay. So, the next thing that we will do is basically kinetic interpretation of temperature, right. So, you must have realized, like, so far we have not really talked about the term temperature, but it is so fundamental to thermodynamics. So, what it is, right. So, let us try to understand what pressure is. Okay. So, remember, so what we will do is we will start with this expression. So, I will just rewrite it here. So, this is 1 by 3 m n by v times v squared average, and what I will do is I will rewrite it in this way. So, 2 by 3 times capital N by capital V times 1 by 2 m v squared average, right. And you must have realized what is this quantity. This is since v squared average is the average root mean squared velocity of individual molecule. So, half mv squared. So, this term is basically the average kinetic energy of a molecule, right. So, what we will say is, so let 1 by 2 mv squared average be epsilon, which is average kinetic energy of a single molecule, right. So, therefore, we can just rewrite this as follows: P equals 2 by 3 2 by 3 n by V epsilon, right. So, now we will basically define another quantity which we call temperature, right. So, remember this is just a definition. So, by definition or even before that. So, remember like we started with the postulate of kinetic energy, we said that thermal energy is the one which causes all the molecular motion, right. So, therefore, we basically started with the fact that if there is anything like temperature exists, it is linearly proportional to the average kinetic energy, right. So, basically what we saw, what we started off with was this epsilon, which is the average kinetic energy. This is proportional to some convenient parameter which we call temperature, right. And this is just a proportionality sign, and we can convert this into equality in this way. So, epsilon equals, let us call it 3 by 2 kBT, where 3 by 2 kb is just a proportionality constant. Okay, so this is just a proportionality constant which tells us like how the kinetic energy, average kinetic energy of a molecule scales with the temperature of the gas, and by definition temperature is just proportional to the kinetic energy. So, I want to stress at this point maybe one more time, right. So, therefore, therefore, what we can see is so if we substitute this epsilon here, so we get so therefore if we substitute this epsilon here, so we get PV equals 2 n times 3 by 2 kBT, right. So 2 by 3 n times and this is nothing but n kBT, right. So, let me rewrite it in this way. So, PV equals n kBT, and this is an important result which I am sure most of you must be familiar with. This is known as ideal gas equation, right. So, this is a familiar result of ideal gas equation, that the product of pressure and volume is equal to the number of molecules times its temperature times the proportionality constant, which is known as Boltzmann constant, right. So, here Kb has a special name, it is known as Boltzmann constant. Right. So, it is a fundamental constant of the nature. All right. So, now, so this is for any n number of molecules, right. So, we can rewrite, okay. So, we can now take a special case. So, for 1 mole of gas, what is your n? Your n is basically Na, and what is Na? This is Avogadro's number. And this is, as you know, it is 6.023 into 10 raised to the power 23 per mole, right. So, this is another fundamental constant. So, therefore, our ideal gas equation becomes PV equals Na kBT, right. And since Na is a fundamental constant, Kb is also a fundamental constant. So, we can generate another constant which is also a fundamental constant. So, I can, so what I can say is, so let us call Na times Kb equals R, and this is known as ideal, is gas constant, right, gas constant. So, therefore, we can rewrite this as PV equals RT, right, and this is the ideal gas equation. So, ideal gas equation for 1 mole of gas, all right. And if you have, and if you for mu moles, so this takes the form PV equals mu RT, right. Okay. So this is an important result. Okay. So now let us talk about numbers a little bit, right. Again, all these proportionality constants, since they are fundamental constants, they can be experimentally measured, right. And R was experimentally measured to be as follows. So the value, value of R from experiments. So R comes out to be 8314 joule per kilomole per Kelvin, okay, or you can rewrite it as this 8.314 joule per mole per Kelvin, right. And remember our Na also, Na was Avogadro's number 6.023 into 10 raised power 23. So therefore our Boltzmann constant is nothing but so the Boltzmann constant is so from here we can get the value of Boltzmann constant, which is R by Na. So therefore our Kb turns out to be 1.38 into 10 raised power minus 23 joule per Kelvin, right. So everything here is in SI units, all right. So and Kelvin is a unit of a temperature, right. So I'll come back to it how we really define this temperature scale, but conveniently we give it another unit, which is Kelvin for the temperature. Okay, so let us maybe quickly summarize before we move on. So what we have done so far, right. So to summarize, so brief summary. Okay, so basically we defined a quantity. Just a second. So defined temperature as a measure of mean kinetic energy per molecule, right. And remember, this is just a definition, right. And also the other important implication of this definition is that for a given temperature, so for example, if we have two gases at the same temperature, then we know for sure that the average kinetic energy per molecule for gas 1 and gas 2 is same, right. So since so what I mean by that is for two gases at the same temperature, the mean kinetic energy per molecule are same. Okay, and the third implication of this can be so remember this is all classical theory, right. So you can imagine that if T goes to 0, your average kinetic energy goes to 0, right. So according to this theory, at T equal to 0, epsilon should also be equal to 0, which means if your if the temperature of your gas is 0, then the molecule will stop moving, and we clearly know that this is not true, right. So therefore we must keep in our mind that there are certain limitations to this theory that's not really valid at very low temperatures, right. So that's something that we should always keep in mind. So it has its own it has its own window where it is applicable, right. We can't really apply it over the entire spectrum of temperatures and so on. All right. So okay. So remember maybe another thing that we can quickly see from this theory is that, remember, so we wrote half mv squared, average was 3 by 2 kbt, right. So from here we can define the v squared average and its square root, right, which is essentially known as root mean squared velocity, and this is nothing but square root of 3 kbt divided by m, right. And the quantity here Vrms is known as root mean squared. So therefore, we can define the root mean squared velocity of individual gas molecule by this expression, and you can see that m appears in the denominator, right. And since we know all the values here, so we know the value of temperature, we know the fundamental Boltzmann constant and mass of every gas molecule. So we can estimate for a given gas what is the typical speed of every individual molecule, right. And maybe it's very straightforward to do that. So maybe we can, what we can do is we can do a little quick little exercise to estimate the root mean squared velocity for various typical gases, all right. So let me make a table. So for example, say you have a hydrogen gas, helium gas, nitrogen and so on. So we can take few examples, argon, carbon dioxide and so on, right, and they all have their certain molecular weight, right. So maybe, so this is a gas, so this is molecular weight which is m, right. So I am writing, okay, so this molecular weight in atomic units is basically 2, 4, 28, 32, 40 and 44, and if you plug these numbers here, so you can get Vrms for these gases to be 1934, for this gas to be 1367, 517, 483, 433 and so on, right, 412. Okay, so it's a very straightforward exercise, and these Vrms is in the units of meter per second. Okay, so this theory actually gives us expression to estimate the velocities of typical gases that we typically encounter. All right. Okay. So the next thing that we can discuss about is the comparison. Okay. So far we have done a theoretical formulation. We have estimated the terms like pressure for an ideal gas and its root mean squared velocity. So let us see how good is this theory, right? How does it compare with experiments, right? So what we can do is so comparison of kinetic theory with experiments. And when we say kinetic theory, so I will keep this expression in mind, right. So PV equals NKBT, right. So this is the ideal gas equation that we got from the kinetic theory. All right. So experimentally there is something known as Boyle's law, right, and Boyle's law basically states that for a given temperature, okay, so at constant temperature the pressure is inversely proportional to volume, all right, and this is an experimental fact. Okay, so people performed very controlled experiments for various gases, and they saw that this is true, right. So if I plot pressure on the y axis and volume on the x axis, so at a given temperature they observed that the pressure decreases with volume, right. So as we increase the volume of the gas, the pressure goes down. Okay, so, and this is at certain temperature T1, okay, and if you change the temperature you get a different curve at say T2, and in this case T1 is greater than T2, okay. So, this is what they observed experimentally. In fact you can see that this is in accordance with the ideal gas equation that we obtained from the kinetic theory, all right. And typically these curves are known as isotherms, okay. So, these constant temperature curves for P and V are known as isotherms, okay. All right. The other important experimental observation was known as Gay-Lussac's law. Gay-Lussac's, okay. And here they again performed many experiments on various gases, and they saw at constant volume, all right. So, the pressure of the gas is proportional to its temperature, okay. So, what that means is if you now again plot the pressure as a function of temperature, right. So, they are linear, they are proportional to each other. So, there will be linear curves, right. So, again, so if we perform this experiment at certain volume V1 and perform this experiment at V2. So, in this case V1 is greater than V2, right, and such curves are known as isocores, okay. Again this is in accordance with the ideal gas equation, all right. And the third observation was known as Charles' law, okay. And again so here they performed experiments at constant pressure. So, at constant pressure so the volume of the gas was proportional to the temperature, all right. And again I can plot it here. So, let us call so the volume on y axis and temperature on x axis, and since they are linearly proportional, so we will get again linear curves. So, this is at some pressure P1, this is at some pressure P2, and in this case P1 is greater than P2. And since these are curves at constant pressure, so these are also known as isobars, okay. So, these curves in PV, PT and VT plane have special names which are isotherms, isocores and isobars, all right. So, therefore, the kinetic theory has does predict does match with experiments over certain range, all right. Okay, so another implication of kinetic theory is as follows, which is known as Avogadro's law. Okay, so Avogadro's law. And what is the statement of this law? Okay, so it says at constant temperature and pressure, okay, equal volumes of two gases contain equal number of molecules, okay. And this again can be very easily seen from the ideal gas equation, right. So, remember we obtained, so remember the equation PV equals 1 by 3 m n v squared average, right. And for gas 1, okay, so this can be written as P1 V1 equals 1 by 3 m1 n1 V1 squared average, where P1 V1 n1 corresponds to the pressure. So, pressure, volume, mass, number of gas molecules and the mean squared velocity of that particular gas. And for gas 2, we can write P2 V2 equals 1 by 3 m2 n2 v2 squared average, right. And what is the statement of Avogadro's law? At constant temperature and pressure. So, which means if the temperature and pressure for both the gases is same, okay. So at same temperatures, we know that so basically half m1 v1 squared average is equal to half m2 v2 squared average, and also we are given that the volumes are constants and pressures are also constant, right. Also P1 equals P2, V1 equals V2, right. So, if you plug that back here, it is very trivial to see that in this case N1 has to be equal to N2, right, and this is the Avogadro's law, right. Alright. So, if you are given if you have two gases which have the same pressure, same volume and same temperature, then the number of molecules in two gases have to be equal to each other. Alright. Okay. So, so let us move on to like I promised, what do we really mean by the term temperature? So, remember, this is just a definition, this is just a convenient quantity that we related with the average kinetic energy of a gas molecule. Okay. So, let us talk little bit about the temperature scale. So, how is it measured? All right. Okay. So, we'll go back to Gay-Lussac's law, right, which said that the pressure of a given gas is proportional to its temperature at a given volume, right. So, from Gay-Lussac's law, at constant volume, the pressure is proportional to temperature, right. And this is actually quite convenient, because if you want to determine the temperature of a gas, you can just do a quick experiment by keeping the volume of the gas constant and just measure the pressure, and that will give you a measure of the temperature, right. So, let us see how do we do that, right. So, we can write this equation in general as follows. So, this can be written as P equals AT plus B, where A and B are constants. And what are these A and B? So if I just plot this pressure versus temperature, so like I said, it is just a straight line, right, over certain range, but you can always like extrapolate it, right, and the A will basically be the slope of this curve, and B will be the intercept or the pressure at intercept at t equal to 0, right. So, this is a convenient way to see that. Okay. All right. So, so let us again look at a few experiments. So, experimentally it was observed. Okay. So, let me draw this plot again. So, pressure versus volume, and what experimentalists observed was as follows. So, remember, we always had this Celsius scale, right. So, we called at atmospheric temperature the water freezes at 0 degree Celsius and it boils at 100 degree Celsius, right. So, what they did, they took various gases. So, let me just call it gas 1, gas 2 and gas 3. So, let me call it gas 1, gas 2, so maybe I should, so gas 1, 2 and 3, and they performed this experiment for various gases at constant volume, right. They all had different slopes, but they saw that when they extrapolated these curves, so they all met together, like intersected at certain point which is minus 273.15 degrees Celsius. Okay. So, this is the extrapolation, right, and you can extrapolate it further. Okay. And basically this is, sorry, so maybe I can, okay. And here sorry, this should be the temperature, okay, and this is basically 0 degrees Celsius, and there is somewhere here you have 100 degrees Celsius, right. And they used water as a convenient way to define the Celsius temperature scale. So 0 degrees where water freezes and 100 degrees is where the water evaporates into steam. Okay. So basically it was observed that these isocores for various gases intersected at a tip temperature of minus 273.15 degrees Celsius. Okay. And which basically corresponded to pressure being 0, all right. So where pressure was 0. Okay. So therefore what we can do is we can now put these values here. So therefore we can write 0 pressure as minus 273.15 times A plus B, right. So these are unknown constants, they are different for different gases, and from here we can see that our B is nothing but 273.15 times A, all right. So therefore now we have the value of B in terms of A, we can substitute that into the general form. So we can write our pressure as, so if you just substitute B here, so you get temperature in the scale of degree Celsius plus 273.15, all right. So this is what we get. So now let us define a new temperature scale. So define a new temperature scale, okay, and let us call it temperature in the units of Kelvin, right. So this is basically temperature in the units of degree Celsius plus 273.15, all right. So therefore we can write this equation. So this equation basically becomes P is equal to A times temperature now measured in the units of Kelvin, okay. And again, so remember now we have to we have an expression that the temperature scale in the Kelvin units is proportional to the pressure of the gas at certain temperature, but we have to benchmark it against something, right. And one of the most convenient ways to do that is to use the triple point of water, okay. So we will come back to all these concepts later, but basically triple point is that special temperature and pressure point where all three phases of water coexist, right. So where you can see solid, liquid and gaseous water at the same time, right. So basically for benchmarking, use triple point of water, okay, and triple point of water corresponds to certain pressure which is triple point and certain temperature, let us call it temperature which is triple point, and it turns out this temperature is 273.16, okay. It's 0.01 degrees Celsius, slightly higher than 0 degrees, okay. So if you put that here, so we can rewrite this equation as P triple point equals 273.16 times times A, right, because T triple point of water is 273.16, right. So therefore from these two equations we can write P by P triple point equals T in Kelvin units divided by 273.16 So, which implies our temperature in Kelvin scale is nothing but 273.16 times pressure of the gas divided by pressure of the triple point of water, all right. Okay. So, this is a convenient formula where we can calibrate the temperature of a gas with the measurement of the pressure, right, in this way, all right. So, basically what this tells you that the change in temperature of the gas is actually proportional to the change in temperature, change in its pressure, and this is a convenient way to convert that pressure into the scales of temperature units, all right, in Kelvin units. Okay. And clearly you can also see that as the temperature, as the pressure goes to 0, the temperature goes to 0, right. So, the 0 Kelvin, the temperature in the Kelvin, on the Kelvin scale, the 0 Kelvin corresponds to the temperature where the observed pressure of the gas just goes to 0, all right. So, it's really a linear scale of the temperature as we wanted, right. So, we wanted our kinetic energy of the gas molecule to be proportional to the temperature, all right, linearly proportional to the temperature. This technique or this way of defining temperature, maybe I can write here, is also known as constant volume gas thermometers, right. So, remember in order to do all this we have to have the gases at constant volume, right. So, this is also at constant volume, right, because we are talking about isocores, all right. So, I hope that is clear. So, this is how we define the temperature scale in the units of Kelvin, all right. Okay. So, now let us take a very few like one interesting example which all of you encounter at home every day, all right. So, let us talk about an example. Okay. So, let us talk about some numbers. So, we have been talking about pressure, temperature and so on, but let us get the feel of it, right. So, what are these typical values? Okay. So, I hope all of you cook rice at home, right. So, what you do is you typically put various, like some rice in the water, right, and put it on stove and heat it up, right. So, the example or the question that we are trying to address is what is the pressure exerted by exerted in the rice cooker, okay, either cooker or any container where in which you are cooking the rice, right. So, let's typically let's use some numbers that we use typically at home, right. So, typically we use water which is like 1 liter, right. So, typical volume of water when we cook rice is about 1 liter, right, and in the SI units is nothing but 10⁻³ meter cube, right. And we typically heat it up this container to like 100 degrees Celsius or something where water starts boiling, right. So, you have to boil water in order to cook rice, okay. So, the temperature of cooking is about, let us just round about this number to 400 Kelvin, right. And typically the volume of your container, so volume of your, so this is a lid, so let me color it differently maybe. So, this is the lid, okay. So, this is the lid. So, typically the container volume or the cooker volume is about 2 liters, right. So, let us just estimate these numbers, 2 liters, which is 2 into 10⁻³ meter cube. And when we cook rice, it's not like the entire water evaporates, it's just the fraction of that water that you have used to cook rice, right. So, typically like let us assume 10% of water turns into steam, right, but rest of the water is boiling, but it is still in the liquid state, but it is the gas which exerts all the pressure, right. So, let us assume fraction of water converted into steam. That is like that is like 0.1 liter and this is like 10 milliliter, right. And since the density of water is 1 gram per 1 kilogram per liter, so this is just 10 grams, right. And in terms of and since we are talking about water, how many moles of water it corresponds to? The molecular weight of water is 18. So therefore, this is equal to 10 divided by 18 moles, and this is 0. I think 556 or something mole, right. So now all we have to do is we have to plug these values into the ideal gas equation, right. So remember your ideal gas equation is PV equals mu RT, right. So this is the ideal gas equation and we'll just plug these value. So mu is 0.056. So R, as we know, the value of R is 8.314. So maybe I should, so this is in mole, right, times R 8.314 joule per mole per Kelvin times temperature, which we assume to be 400 Kelvin, divided by the volume of the container, which is 2 into 10 raised to the power minus 3 meter cube, right. And you can see the units also get cancelled, and you have eventually, so the answer that you will get, you can verify this, we get something like 10 raised to the power 6, and joule per meter cube is nothing but Newton per meter squared, right, and this is the units of pressure, right. So this is a typical value of pressure that is produced when you are cooking rice, right. And let us compare this number with something, right. So remember, we in our atmosphere, the atmosphere is always exerting certain pressure on us, and the typical value of that atmospheric pressure is, so P atmospheric typically is about 10 raised to the power 5 Newton per meter square, right. And you can see that pressure that you create in a rice cooker is 10 times greater than the atmospheric pressure. So therefore, if you are cooking rice or any dal or those lentils or any vegetables, and when you heat up this water, so enough pressure is created, so that is why either the whistle goes up or the lid basically just comes off, right. So the pressure is about 10 times the atmospheric pressure, right. So I hope this gives you some perspective of numbers when we basically the things or kind of simple experiments that happen in your kitchen all the time. Okay. So in the last few minutes, so let us basically talk about few terms which we will use repeatedly in this course, like thermal equilibrium or first law of thermodynamics, right. So let us try to understand what is thermal equilibrium in the picture of kinetic theory, right. So what is thermal equilibrium? All right. So this is something that I am sure you are all aware of. So when we say two systems are at thermal equilibrium, that means their temperatures have to be same, right. So say we have a container which is completely insulated, right. Insulation means no heat can leak out of this container. So we typically schematically draw insulation in this way, right. So this is insulated wall, and let us say there is another wall here which separates two gases, right. So say you have some certain gas molecules on this side and other gas molecules which have maybe smaller molecules on this side, right. And let us say the temperature on this part of the container is T1 and temperature in this part of the container is T2, right. And it is separated by a conducting wall, which means it can transfer the temperature from one side to the other, right. And let us say initially our T1 is not equal to T2, right. So, there is temperature mismatch. And also let us assume on the left side of the container, the mass of molecules is m1 and they are moving with v1 squared velocity, and on this side we have m2 and v2 squared average, all right. And when we say initially T1 is not equal to T2, remember these are just by definitions we can just write that half m1 v1 squared average is not equal to half m2 v2 squared average, right. But at equilibrium, as we know, we say two things are at equilibrium if they have the same temperature, T1 equals T2, which implies m1 v1 squared average is equal to m2 v2 squared average, right. So, this is the condition for thermal equilibrium. If the average kinetic energy of a gas molecule on the left of gas 1 is equal to average kinetic energy of molecule in gas is same as gas 2, then they are at thermal equilibrium, right. So, now let us try to understand how this actually happens, right. So, let us assume our T1 was greater than T2, right, which means these molecules on average have much higher kinetic energy than the molecules on the right side, okay. So, therefore, what they will do is, so remember they are due to finite temperature, they are constantly moving around, they are hitting the walls of container, but since this is an insulating wall, they do not really lose any energy. But remember the conducting wall is also made up of many atoms or molecules, right, and every time these molecules make collision with this, so that kinetic energy gets transferred to these molecules in the wall, and since these molecules on the other side of the partition, they are also moving. So, these molecules will impart that energy into these molecules, right. So, just remember, so you have certain molecules which are moving and jiggling much faster. So, they are just transferring that energy, kinetic energy, from left side of the container to right side of the container, right. So, if I can just maybe draw, so there is a net, flow of kinetic energy from left to right, right, if your temperature T1 is greater than T2, and the energy is being transferred just due to the collisions, right, repeated collisions that these molecules are making with the conducting wall, and then that energy gets transferred to the other side, right. So, therefore, there is maybe transfer of kinetic energy from left to right. And that is all we mean by the term thermal equilibrium. So, when there is no net transfer of this energy, then you are at thermal equilibrium, right. And maybe we can also now define another quantity. So, this transfer of kinetic energy from left to right is known as heat, right. So, transfer of energy, or maybe I can write here, transfer of energy by definition is known as heat, right. And what is heat? What is the simplest definition of heat? Heat is energy in transit, okay. So, when kinetic energy or energy is transitioning from one point to the other, there is a flow of net energy, and that flow is known as heat, okay. So, there is this very subtle difference between temperature and heat, okay. So, you should always remember temperature is something which is inherent to any system, right, but heat is the transfer of that energy to another system, alright. Only if there is a transfer of energy from one point to the other, you can talk about heat, alright. So, as you know, like so if both sides of this container are at the same temperature, there is no net heat flow, right. But if they are at different temperature, there will be flow of heat, okay, flow of energy, okay. And in the same spirit, we can also maybe talk about another important concept, which will basically move into this concept again later. This is the first law of thermodynamics, right. So, first law of thermodynamics. right. And what is first law of thermodynamics? So, typical statement that we use is, so energy can neither be created or destroyed, so total energy of the system of the universe remains constant. Okay. So, let us try to understand it from kinetic interpretation of matter, right. So, let us say we have a container, right, and this container contains certain gas molecules, right, large number of gas molecules, and they all are moving with certain kinetic energy. So, there is certain temperature associated with it, right. So, let us define some terms here. Okay. So, there is a term which is known as internal energy, which is basically total kinetic energy of the gas, right. So, we know there is so every molecule has certain kinetic energy, you sum that up, right. So, you just take the you just sum it over all the gas molecules, whatever total energy you get, that is known as the internal energy, right. Now what we do is, let us bring some heat source close to this container, right. So, maybe let us bring a candle, right. And what is a candle? Candle is a another source of energy which is at much higher temperature, right. So, candle is hotter, right. So, there is a flame which is much hotter, and what is the heat means? That means the molecules around the candle flame, they are moving at much higher kinetic energies than the gas itself, right. So, there are these gas molecules close to the candle, which are at much higher kinetic energy. So, what they will do is, there will be a net transfer of this heat from candle into the gas, right. So, transfer of heat, right. So, okay, so that there will be a net transfer of heat, and what that heat will do is, that will increase the kinetic energy of these gas molecules in the container. And as a result, if we have a movable wall attached to a piston, right. So, say there is a movable wall attached to a piston. So, some part of this additional kinetic energy will, so these molecules, remember, they will collide with these walls, and as a result this wall will expand, right. It is similar to how in your rice cooker the lid was coming off, right. So, the gas was moving this lid, so there was physical work that was being done, right. Okay. So, this internal energy is typically denoted by term U, right, and heat, I do not know whether I wrote here. So, heat is typically denoted by symbol Q, right. So, heat is denoted by symbol Q, and work, okay, and these molecules, when they collide with this wall, they will do certain work, right. So, heat is denoted by symbol Q, and work is denoted by symbol W, right, and work is mechanical in nature, right. So, there is a object which is physically moving from one point to the other, all right. So, according to first law, now it is very easy to see that change in the internal energy of this gas. So, let us call change in internal energy delta U, right. What is that change? That is sum of the heat that is supplied from candle to the gas, which is delta Q, minus the amount of work done by this gas onto the wall, right. So, let me write. So, this is change in internal energy, this is heat supplied to the gas, and this is work done by the gas, right. So now this is you might be familiar with this. So, this is basically typical statement of first law statement. So, basically this is just the first law of thermodynamics, right, first law of thermodynamics. and this can very easily be like at least visualized or seen in your mind very easily, that there is a source of kinetic energy close to the candle, and part of that kinetic energy is used to increase the kinetic energy of gas molecules, but some of that kinetic energy is being dissipated into the work which is done by these gas molecules on the movable piston, right. So and that basically these three terms, since energy cannot go anywhere, right. So all the energy from the candle has to be either utilized as the internal energy of the gas or the work done by the gas on the system. So we get this very elegant looking equation, which is basically the statement of first law of thermodynamics. Okay. So yeah, so in the next class we'll continue with this kinetic formulation, and we'll basically derive the distribution of molecular speeds. Okay. So see you in the next class.